We've seen that we can use polar coordinates for a double integral in 2D space, but we can also use polar coordinates for a triple integral in 3D space if two of our coordinates are nicely described using polar coordinates. So here's an example of that. Let's find the integral of this function, x times z, over this cylinder, which has radius 3 and extends from z equals 0 to z equals 4. So if you look at the shape of this region just in the x and y direction, right, just in the xy plane, there's this circle with radius 3, and so that's in the x and y direction, and in the z direction, it's a cylinder, so this just goes straight up, right? So if we wanted to, in the x and the y direction, in the xy plane, I should say, instead of using Cartesian coordinates, x and y, we could use r and theta, right? So to describe this region using this setup, well, in the xy plane, our radius goes from 0 out to 3, so we'd have 0 less than or equal to r less than or equal to 3, and then the angles that we need to cover the circle that is the base of this cylinder is from 0 up to 2 pi, so theta is going to go from 0 to 2 pi. Theta is going from 0 to 2 pi. And then z, well, z is still just the regular Cartesian z coordinate, and that's going from 0 to 4. So z is going to go from 0 to 4, and you can see that we have three coordinates, which is what we would expect in 3D. So we can actually write this triple integral. So writing this triple integral, we would have the integral over this region of x, z, dv. So essentially what we're doing here is we're writing the z integral separately. I'll write it on the outside because I can, because the bounds for the z direction are constants. If your z bounds depended on x and theta, you could put or r and theta, you could put the z integral on the inside instead of on the outside. So, but for this one, since the z bounds are constants, I'll put that on the outside. Right, we have this function that we're integrating xz, and so we have, I'll write dA. This dA is in the xy plane. Okay, and then the region in the xy plane is the circle with radius, or the disk, I should say, with radius 3. Disk radius 3. Okay, but this inside integral, we're just going to use polar coordinates for it, right? We have nice bounds for this disk in the xy plane, and crucially, we know what dA is in polar coordinates. It's r d theta. So we can rewrite this integral using polar coordinates for the xy plane. Excuse me. Okay, so this is going to go from 0 to 4 in the z direction, and then, so that's dz. And then dA is r d theta. So my theta bounds are going to be from 0 to 2 pi. And my r bounds are going to be from 0 to 3. Okay, and the integrand was x times z. Z is still z, but x, because we're using polar coordinates in the xy plane, x is r cosine theta. All right. So we can evaluate this triple integral instead of the original one. This triple integral is especially nice because the integrand is a product of a function of r, a function of theta, and a function of z, and all of the bounds are constants. So we can split this up into 3 different integrals, one for each coordinate. So the integral from 0 to 3 of z dz times the integral from 0 to 2 pi of cosine theta d theta times the integral from 0 to 3 of r squared dr. And And this all is going to come out to be 0 because this integral right here is going to be 0, right? This is going to give us sine theta from 0 to 2 pi. That's going to be 0. So this whole thing turns out to be 0. Okay. One nice thing about this trick of using polar coordinates for two of your coordinates is that it doesn't have to be the xy plane. Right, we chose polar coordinates for the x and y directions just because this region is especially nice, this region is especially nice if we use polar coordinates for the xy directions. If instead we have an example like this with a half cylinder sitting on the xy plane with radius 4, length 10, and a certain density function, and we want to find the mass, well, if you look at this region, so if this is the xy plane, it sort of looks like this. Right, it's a half cylinder like this, and because the density function doesn't depend on x or y, we can slide this shape anywhere around the xy plane to make it convenient. So let's put the origin right here, I guess. The x-axis going out this way. So I guess this is going to go out to x equals 10. And since the radius is 4, it's going to go from minus 4 to 4 in the y direction. So for this, the way that I have this, this shape situated on the xy plane, it looks like if we look just at the yz plane, the shadow that this shape casts is a semicircle. And so if we use polar coordinates for the yz plane, this region will be very easy to describe. Right, using polar coordinates for the xy plane would be a mistake because the shadow that this shape casts on the xy plane is this rectangle, and that would be very difficult to describe using polar coordinates. So by using polar coordinates for the yz plane, we can take advantage of the nice polar shape that this takes in the yz direction. Okay. So let's see. To find the mass when we have a density function, right? We just need to do the triple integral of our density function dv. We're going to write this as, let's see, in the x direction we're going from 0 to 10. So we'll put that on the outside, and then we need to write dA in the yz plane, right? Because dv is dA times dx if this dA is in the yz plane. And since we're using polar coordinates for the yz plane, dA is just going to be r d theta, of course. Okay, so now we need theta bounds. Let's see. So in the yz plane, right? We actually have a choice on on how we want to set up our polar coordinates. We can either say that z is r cosine theta and y is r sine theta, or we can do it the other way around and say y is r cosine theta and z is r sine theta. And both of these are possible, but the second way is actually the most straightforward for the following reason. When we worked out how to do double integrals in polar coordinates, right? We had our coordinate system for the xy plane set up in the usual way, so that the coordinate system is right-handed. So if you take your right hand and you align your index finger with the positive x-axis with your thumb pointed towards you and curl your fingers will curl from the x-axis towards the y-axis. So from the first coordinate to the second coordinate. So if you try to do that same thing with this xy plane, align your fingers. So look at the yz plane. Look at the yz plane sort of face on like this. Point your fingers in the direction of the positive y-axis. and curl them, they go towards the positive z-axis, again with your thumb pointed towards yourself. So this is a correctly oriented plane if we use y as the first coordinate and z as the second coordinate. So so since y is playing the polar role that x usually plays, it gets the cosine, and since z is playing the polar role that y is usually playing, it gets the sine. So this is the right way to do it. If you have them backwards, it turns out you'd get a minus sign. I'll let you play with that and see how and why that works. Okay, so at any rate, we set this up this way so that we know how to measure the theta values that we're using. So the positive, since y is our first coordinate for this plane, the positive y-axis acts like theta equals 0, and we're going to go in this plane up to theta equals pi down here. Okay, so our theta coordinates are going to go from 0 to pi, and then of course r is going to go from 0 to the radius of our cylinder, which is 4, and our density function is z squared. Sorry, we can't write z squared. We have to write z in terms of r and theta. So z squared is r squared sine squared theta. And again, this turns out kind of nice because we can split this up. This is integral from 0 to 10 dx, integral from 0 to pi sine squared theta, integral from 0 to 4. This is going to be r squared times another r, that's r cubed, dr. And I left off my d theta here. Okay. So now we can evaluate this. Let's just wrap it up. So integral of dx from 0 to 10, that's going to be 10. Integral of sine squared, so sine squared is 1/2 1 minus cosine 2 theta, right? So this is going to give me 1/2, and now do our integral, we get theta minus 1/2 sine of 4 theta. Sorry, yeah, 2 theta, not 4. Okay, from 0 to pi. And for our r integral, we get 1/4 r to the 4th from 0 to 4. So let's see this. Let's simplify these. 10 times 1/2 is 5. When we start plugging our bounds into this stuff, well, sine of 2 pi and sine of 0 are both 0, so the sine part doesn't contribute anything, and this theta part just gives us a pi. And then when we evaluate things over here, we get 1/4 times r times 4 to the 4th minus 0. Okay, so 5 times 4 cubed times pi, whatever that turns out to be. So the one thing we have to be careful about when using polar coordinates for other coordinate planes is we have to be sure that when we use this coordinate